In this video, we will look at the acidity of alkynes. So just as a brief review, recall that an alkyne has a carbon-carbon triple bond, and then it can have hydrogens on either side of the alkyne, or it can have other alkyl groups that I'm representing generically as R. In addition, there is a terminal alkyne. Terminal alkynes have a proton, so a hydrogen atom, at the end or the terminus of one side of the alkyne. And it's called terminal because now this carbon-carbon chain cannot extend further beyond the hydrogen. Because as we know, hydrogen cannot take a second bond, it can only have one bond. So by that definition then, a terminal alkyne cannot extend any further. This hydrogen cannot be bound to another carbon, making the chain longer. However, on the other side, this is not terminal because this R group can be other carbons, which then elongate the carbon-carbon chain. But either way, the alkyne functional group is the carbon-carbon triple bond, and this hydrogen has special properties that we'll talk about here in a minute that makes the terminal alkynes extremely useful in organic chemistry. So the most important property that I'm referring to is that terminal alkynes are acidic, and they have a pKa of approximately 25, which isn't particularly acidic, but there are bases that are strong enough to abstract this proton, and then once that proton is abstracted, you can do interesting chemistry, interesting reactions with the resulting product. Now I want to compare the terminal alkyne's acidity compared to some other functional groups that we've already seen. So as I just introduced, a terminal alkyne has a pKa of approximately 25. This can vary somewhat depending on the identity of R through the inductive effect and things of that nature. So 25 is our benchmark that we'll use for alkynes, but it can vary depending on the particular compound. But that is not particularly acidic, especially when we compare it to the pKa of water, which is approximately 16. So, and remember, pKa is a log scale. So 25 to 16, that's a 9 difference, but it's 10 to the 9. So water, the protons on water are 10 to the 9 more acidic, or a billion times more acidic than the alkyne proton. And then here we have phenol. This is a pKa of about 10, which is even more acidic than the water protons. And then here's acetic acid from our carboxylic acid functional group, and this proton is even more acidic than the remainder. So my point here is that alkyne protons are acidic, but they're not particularly acidic. So to abstract this proton, you need an extremely strong base, and we'll talk about the identities of some of those bases that can abstract this proton in an efficient and productive way. So as I just mentioned, some strong bases can remove the terminal alkyne proton, but what are the identity of some of those bases? Well, one of them is this sodium amide, which is NaNH2. And the reason this is particularly acidic is we know that the pKa of ammonia, NH3, is approximately 40. I think it is about 37 or 38, something in this region, which that's extremely high. So that means the weaker the acid, the stronger the conjugate base. So here we have ammonia, NH3, so its conjugate base is NH2. So since the pKa of these protons are so acidic, that means that this base is extremely basic. So because of that, this is NH2 is a stronger base than this alkyne with a negative charge. So a base like sodium amide can undergo this type of acid-base chemistry where the lone pair on the nitrogen can come in and form a bond with this hydrogen and then cleave the electrons onto the terminal alkyne carbon, and that results in a lone pair or a carbanion on the terminal alkyne carbon, making this negatively charged, and then the sodium will balance out the charges here, and we're forming this new bond to nitrogen, making NH3, making ammonia. So the point here is that you need an extremely strong base to abstract this proton. Typical bases like T-butoxide or sodium hydroxide are not going to be strong enough to remove the proton. And how I've represented it here, and this is pretty common in the literature and textbooks that you'll see is that the equilibrium is lying very far to the right or in the forward direction, forming this carbanion, because I'm representing that by the equilibrium to the right arrow is much larger than the one going to the left. So these are all acid-base reactions are all equilibrium, meaning that they can go and flow in either direction, but due to the nature of the NH2 and the terminal alkyne proton, this is more basic than the carbanion, so it will function in the forward direction. The reaction will proceed as you see it. So there's going to be a lot more of these products available than the reactants. This kind of begs a question of why terminal alkyne protons are acidic. And the reason has to do with the hybridization of the carbons that are involved in the bond to that hydrogen. So if we look here we just have some generic terminal alkyne. This is acetylene with the two terminal alkynes protons, so just one hydrogen on each side of the alkyne, and these are all sp orbitals because there's only two bonding groups to the carbon, so that increases the s character. So an sp orbital has 50% s character and 50% p character, which means that this orbital has more of a negative character because of the increasing s character. So there is kind of a pseudo dipole between the sp hybrid orbitals and the s orbitals involved in the carbon hydrogen bond. So because of that, there is a stabilization of the conjugate base. So due to the orbital hybridization here, when the base comes in and abstracts this proton, we get a negative charge on the carbon, creating a carbanion, which is stabilized due to the nature of the orbital that the lone pair will reside in the sp orbital. So you can think of this kind of like there is a dipole here between the carbon and the hydrogen, similarly to if there was an oxygen or some other electronegative atom. Due to the nature of this carbon-carbon triple bond, the sp orbitals, this becomes somewhat electronegative, causing this dipole, which then explains why a base could abstract it, and it also then explains the stabilization of the conjugate base. The point of all of this is that we can take advantage of the acidity of these terminal alkyne protons to do new reactions and to increase the carbon skeleton, the number of carbons that are in a particular molecule, because we can create a nucleophile due to the acidity of the alkyne proton. So for instance, if we look at this reaction, we can create a new carbon-carbon bond between the terminal alkyne carbon and this CH3. So I'll illustrate the mechanism here. So first of all, we have sodium amide again. This is a really strong base that we've introduced before. It can abstract the terminal alkyne proton. So that's the first thing that will happen. So we have sodium amide, which has a negative charge on the nitrogen, positive charge on the sodium, and then we have our terminal alkyne proton, which is this one here. So the sodium amide can come in and abstract this proton, specifically the lone pair on the nitrogen, and then we dump the electrons onto the carbanion, to form the carbanion, I should say. So here, the product is this with a negative charge in the lone pair on this carbanion. And now this has become a base and a nucleophile. And by the way, we created NH3 ammonia as a byproduct. That isn't critical here, but sometimes you may need to include that to explain how all of the atoms are conserved and they're still involved in this reaction. So this is now a nucleophile and a base. So the fact that it's a nucleophile, we can react it with a good electrophile, which is exactly what part 2 of this mechanism does, part 2 of this reaction. So here, if we have CH3I, we know that there's a dipole going towards the iodine, so that's a partial negative, and the carbon has a partial positive. So now, this is a good leaving group. Iodine's a good leaving group. This is a good base, or a good base and a good nucleophile, so it can come in and attack to create this new bond. So that's exactly what happens. This lone pair on the carbanion will attack the carbon, and then we will cleave the carbon-iodine bond, forming this product up here. So, and there are byproducts, as I mentioned. There's NH3 in the first step, and now there is sodium iodide, are byproducts. So the point of this is that we can use the acidity of the proton, of the terminal alkyne proton, to create new carbon-carbon bonds, which is extremely useful because there's only a limited number of ways to make carbon-carbon bonds, and this is one of them. We take advantage of the idea that the terminal alkyne protons are acidic. But notice, this is a primary haloalkane. The fact that this carbanion is a nucleophile and a base suggests that we could undergo this type of substitution reaction and an elimination reaction depending on the nature of the electrophile. So in this case, because this is a primary electrophile, the substitution reaction will predominate, but if this was a secondary or tertiary haloalkane, we would not get the substitution reaction. So, as I just mentioned, this type of reaction where we increase the number of carbon-carbon bonds that are in our molecule is only possible with primary haloalkanes. If you use a secondary haloalkane, like in this example, you will get primarily the elimination product, and I'll work through that here. So what I'm showing is we want to use this secondary haloalkane to create this carbon-carbon bond, but I'm saying that there's 0% yield of this, and this may be slightly off. There may be 1 or 2, 3% of this was actually going to happen, but it's so small that it has no utility really in the lab. So let's go through this mechanism. So again, we have sodium amide. That is a very strong base, so it's going to abstract the alkyne proton, which is the first step again. After that happens, we form the exact same carbanion that we had in the previous example. So now I'm not showing the carbon explicitly, but this negative charge is on that terminal alkyne carbon. And then there's the sodium, of course, and our ammonia that is a byproduct. Now, when this reacts with the secondary haloalkane, the primary reaction is not going to be the substitution, because what we want to do is use this negative charge, the lone pair on this carbon, to create a bond here and then dump the electrons onto this iodine leaving group. That would create this product. But that is not going to happen because there is a base nature. This is a base as well as a nucleophile, and acid-base reactions are faster than substitution reactions. So what's going to happen is this will function as a base, abstract this proton, and then dump the electrons here, forming an alkene, and then create this leaving group. So the primary products then are going to be this one, this alkene, which is formed by this new bond here that this arrow represents. We also have sodium iodide that was formed when this leaving group cleaves, and we reform the alkyne that we started with. And this will happen much more than the substitution reaction because this is a very strong base. So therefore it's more likely to function as a base than a nucleophile. For the remainder of the video, we will look at several questions tying these ideas together in exam types of questions that you'll see on an exam or quiz or some other assessment. So first, we need to understand that the acidity is only in the terminal alkyne protons. So we need to be able to recognize what is terminal and what is not. So the question here is, are there any acidic protons in the following molecules? So here, we have a T-butyl group, which is a carbon bound to 3 methyl groups. Then we have our alkyne and another T-butyl group. So therefore, there's no hydrogen on either of these alkynes because this is an internal alkyne, and because of that, there is no acidic proton. So for these alkynes, you're simply looking for an terminal alkyne proton. That will be your acid. If not, there is an acidic proton. Here we have a cyclopentane ring bound to a carbon-carbon triple bond where there is a terminal alkyne proton here, so this will function as our acidic proton. So this is a bit of an introduction of the types of questions that you'll see, but you need to be able to recognize this quickly. Because, for example, if you wanted to react this with a base and then a nucleophile, nothing is going to happen that you want because there's no acidic proton on the alkyne, so you're not going to create the carbanion nucleophile that you want. So this would be not a particularly useful alkyne for this acidic substitution type mechanism that we've been looking at in this video. Now, the next type of question puts together the idea that you need a very strong base to remove the alkyne proton, the terminal alkyne proton. So that is how you could predict which direction the equilibrium will lie, which is this specific question. So if we look here, we have a terminal alkyne. Here's our terminal alkyne proton. We have sodium hydroxide, and then we would form the carbanion and water, where the mechanism would be this negative charge on the hydroxide would abstract this proton, and then that would create the products that you see here. So now the question is hydroxide a strong enough base to remove that alkyne proton? And the answer is it's not. And the reason that we can explain that is we know the pKa of water is about 16, and the pKa of our alkyne, of a generic terminal alkyne, is about 25. So remember, the acid and its conjugate base have a relationship. So the stronger the acid, so lower the pKa, the weaker the conjugate base. So here we have water, H2O. So if we remove a proton to make its conjugate base, that would be hydroxide. That is going to be a weaker base than if we remove this alkyne proton, because remember, it is the relationship between the acid and the conjugate base. So since this is a weaker acid, its conjugate base is stronger. This is a stronger acid, so its conjugate base is weaker. So this equilibrium is actually going to lie to the left, or the reverse direction as written, because this is a stronger base, so this will actually remove the proton from water and reform sodium hydroxide and the alkyne. All right, here is the last type of question that we'll look at, and this is simply just predict the products and explain its formation. Remember, in organic chemistry, when you see explain its formation, that means draw the mechanism for the creation of the product. So, first thing we notice is we have a terminal alkyne proton and an extremely strong base. So that is the theme of this video, is that we're going to remove this acidic proton with a strong base like sodium amide. So this negative charge, the lone pair on that nitrogen, will come in, remove that proton, and then create the carbanion, this one here. Okay, and then also we create we create ammonia. Now, this can react with an electrophile because this is a strong nucleophile. Remember, the electrophile must be primary in order to get the substitution reaction as a primary product. And in this case, we're reacting it with a propyl iodide or iodopropane. So what's going to happen is our carbanion will function as a nucleophile, create this new carbon-carbon bond, and then we'll dump the electrons onto our leaving group, and we create our final product, which extends the carbon skeleton, right? Always count your carbons to make sure that you have the correct number that you started with. So here we have our T-butyl group, carbon-carbon triple bond, and then we added 3 carbons. These 1, 2, 3 carbons, 1, 2, 3 carbons. So this is the final product. And again, we have byproducts of sodium iodide and ammonia. Here we have one more question where it predict the products and explain its formation. So again, we have a terminal alkyne, which notice is key for these types of reactions. And then we have another primary haloalkane. It has this cyclopentane group bound to it, but it's still primary at the electrophilic position. So this is likely going to undergo another substitution, the substitution reaction where you remove the acidic proton. So we have our sodium amide. This will remove the proton here, dump the electrons onto the carbanion, like this. Again, we have our sodium counter ion and NH3 as a byproduct. And then we react this as a nucleophile with our electrophile, which is this iodide cyclopentane group. So we have our lone pair coming in, creates this new carbon-carbon bond, and dumps the electrons onto the iodide, which is our leaving group. So the final product is going to be this internal alkyne with one carbon and then the cyclopentyl group. So always count your carbons to make sure that it is correct. So here we have our CH3, the internal alkyne, then one carbon, and then two, which is bound to the cyclopentyl, which I have drawn like that. If you're confused why I drew it like this, in this case it simply doesn't matter because there's no substituents anywhere else on the cyclopentane. So this is perfectly acceptable. If there was substituent somewhere, then you would have to consider that in the final product that you draw, but here it was not necessary. So that is all I have for this video. Hopefully you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have any questions, leave them in the comment section below and I will get to them as soon as I can. So with that, I hope you have a good day and I'll see you all in the next video.